So for this video, we're going to work on the following problem here. So this says, use the rational zeros theorem to find all the real zeros of the polynomial function, and then use the zeros to factor f over the real numbers. Okay, so the rational zeros theorem, what it tells you to do is it says essentially that all of the possible zeros of the function are going to be within the little formula P over Q, where P is your constant, right, of your function, and Q is your leading coefficient. So it's essentially your last number in your function divided by the first number in your function. So we have f of x is equal to 4x cubed minus 11x squared minus 6x plus 9. 9 is our constant here. This is going to represent P. And 4 is our leading coefficient, so that is going to represent Q. So what we're going to do is we have 9 over 4. And what we're going to do is we're going to list all the possible factors of those numbers. So let's start with 9. So when I say all the possible factors of 9, so what are all the numbers that can multiply to get 9? There's not that many of them. We can do 1 times 9, or we can do 3 times 3. That's it. And we don't need to repeat any numbers. All right, so 1 times 9 will give us 9, or 3 times 3 will give us 9. And do the same thing for the 4. So the only way to get 4 is 1 times 4, or 2 times 2. Now, all of our possible zeros are going to come from doing this. So essentially, we need to take everything in the numerator and divide it by everything in the denominator. So it's going to look like this. So we're going to do 1 divided by 1. All right, so 1 over 1, and then do the 1 over 2, 1 over 4. Now do the 3 over 1, 3 over 2, 3 over 4. Then 9 over 1, 9 over 2, and then 9 over 4. And for every single one of these, it could be the positive or negative variation of it. So we have positive 1 over 1, negative 1 over 1, positive 1 over 2, negative 1 over 2, and so on and so forth like that. So when we simplify some of these are going to be able to be simplified, some are not. So for example, 1 over 1, right, we know that that's just a 1, right? So I can put that in as a 1 here. 1/2 doesn't simplify, 1/4 doesn't. 3 over 1, I'm just going to write that as a 3. Let's see, 3/2 doesn't simplify, neither does 3/4. 9 over 1 is simply just a 9, and it looks like that's it. All right, so this theorem tells us that the zeros of our function are going to lie somewhere within all of these numbers. I know it's a lot because we have 1, 2, 3, 4, 5, 6, 7, 8, 9 different numbers here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. We have 9 different numbers here, and we have the positive and the negative variations of it. So technically, this is 18 different possibilities of numbers that can be our zeros. Now, the degree of this function is a 3, so that indicates that at most we're going to have 3 zeros for this function. But we are done with the first part of the question. The first part of the question wanted us to use the theorem to find all the possible zeros of the polynomial function. So that's what this represents right here. But then they want us to use the zeros to then factor f over the real numbers. So what we typically do after this point here is we start testing numbers and testing to see if they are zeros. And we can test that using synthetic division. So essentially we would just go through the list, start with 1, then test negative 1. Then I would probably jump to 3 and then test negative 3, 9, and then negative 9 before jumping into some of the fractions here. So first I'm going to test 1 using synthetic division. All right, so I'm going to put my 1 over here, and with synthetic division we list all the coefficients of all of the terms that we have in our function. So that would be a 4, a negative 11, a negative 6, and a 9. So doing synthetic division here, so we start by dropping down the 4. 4 times 1 is 4, so we put that here. And we add these together. Negative 11 plus 4 gives us a negative 7. Negative 7 times 1 is a negative 7. When we add these together, we get a negative 13. Negative 13 times 1 is a negative 13. And when we add these together, we get a negative 4. That means that 1 is not a 0, because in order for it to be a 0, we would actually have to get a 0 here in our last position when we add. We got a negative 4. So that means that 1 is not a 0 of our function. So I'm going to test negative 1 now. All right, so I'm going to do the same thing. So we have 4, negative 11, negative 6, and 9. Dropping down the 4, 4 times negative 1 is a negative 4. Adding these together gets me a negative 15. Negative 15 times negative 1 is a positive 15. When I add these together, I get a 9. 9 times negative 1 is a negative 9. And when I add these together, I do get a 0. So that means that negative 1 is a 0 of this function. What that's going to allow me to do is it's going to allow me to rewrite my function. And the way that we do that is we start from the back to the front. So because this is a 0, we start at the 9. 9 is our constant. Negative 15 is the coefficient of our x to the first. 4 goes x to the second. And then if we had numbers, it would be our coefficient of x to the third, x to the fourth, and so on. All right, so we write this from the back. So 9 is my constant, and it's a positive 9. This negative 15 represents the coefficient of my x to the first power term. And this positive 4 represents the coefficient to my x to the second power term. And this is my remaining polynomial after we have removed our factor of the negative 1. All right, so it allows us to go from an x to the third power function to an x squared function, which is going to help us because it drops it by 1 degree. It gives us an x squared function here, a quadratic function, which now we can hopefully factor this in order to find the other two zeros. That would be a lot nicer if we could do that than going ahead and testing the rest of the 16 numbers that we haven't tested yet. Especially with a lot of these being fractions, it's going to give us a lot of just ugly work having to deal with the fractions here. So if we can factor it, that's going to be the better thing. So I'm going to factor this using no-fuss factoring. No-fuss factoring tells us for the first factor, repeat that twice, 4x times 4x. Second step, take the first coefficient times the last, so 4 times 9 is 36. We're looking for what multiplies to get 36, but adds or subtracts to get 15. And that would be a 3 and a 12 there. Looking at my signs, these are both going to be negative, since negative times negative is positive, and negative 3 plus negative 12 is a negative 15. Last step in no-fuss factoring is to reduce one or both of your factors. Looking at my first factor of 4x minus 3, 4 does not have anything in common with the 3, so that one cannot be reduced. I'm just going to drop that one down. My second factor, 4x minus 12, 4 and 12 has a 4 in common, so I'm going to reduce it by 4. So when I divide that out, I get x minus 3. So these are my two factors of this function, right? And we're going to say that this equals 0. All right. So what I'm going to do is I'm going to move those right over here, right? Because if these are my two factors of the function, we can then use the zero factor property that says that we can split our factors up, set them each equal to 0, and solve. Solving the first equation, we're going to add 3 on both sides, giving us 4x is equal to 3. And then we're going to divide both sides by 4, giving us that x is equal to 3/4. Our other equation, all we have to do is add 3 to both sides, giving us x is equal to 3. So our three solutions, so we got a negative 1, we got 3/4, and we got 3 as the three solutions to our function here. We were able to factor it, right, and we use synthetic division to drop it down in the beginning to make it a quadratic equation here. Otherwise, that's it for this video.